Hello everyone, welcome to the fifth lecture of module 3. So in the last lecture, we were discussing about inverters based on MOSFET along with a resistive load, right? So we also talked that, because of that resistive load, we had a huge deal of static power dissipation. And also we were discussing since the very beginning that, these resistors occupy a large amount of area. So in this lecture, we would be discussing about, the ways in which we can replace that resistor with other loads. Mostly transistor-based loads or MOSFET-based loads. So different MOSFETs, different modes of MOSFET. So let us go ahead. The disclaimers remain the same. So let us first discuss in detail why exactly do we need to replace resistors in inverters. First reason being, the static power dissipation was huge that we saw in the last lecture. Now the second and the most, I would say, important reason is the monolithic integration of resistors on a chip that requires a large area, and we know that area is proportional to the cost, not proportional. In fact, cost goes as area raised to power 4. It's a function of area raised to power 4 that we saw. So we would always like to minimize the area as well as the cost. So how exactly do we define a resistor? So let's say this is a resistor. So its width is W, length is L, thickness is T, and the current is flowing along this direction. So we define resistance as rho L by A. Here it's simply rho L divided by W into T. Now how basically these resistors are implemented in on chip is that we have like a layer of a metal. It can be a metal, it can be a polysilicon, it can be doped silicon, or it can be undoped silicon, depending upon the range of resistance that you want. So what people do is, if they want a pretty small resistance, they'll draw a metal line and then take two contacts here and here. If they want to have a very large resistance, people will draw a polysilicon line and then they'll take two contacts here and here. So these two contacts are kind of the two terminals of this resistance. And if they want to realize something in between, they can use either doped semiconductor, that is doped silicon, or they can also use undoped silicon. So depending upon what range of resistance we require, we can use metal, we can use polysilicon, we can use doped silicon, we can also use undoped silicon. So this is how these resistances look from top. I mean, this is the top view of it. So this is simply the width, this is simply the length, right? And now what about the thickness and all? So thickness is kind of fixed for the layers. When we are foundry already gives us a fixed thickness of these layers. So since the thickness is fixed, how we define it when we are developing on-chip resistances is in terms of sheet resistance. So what exactly is sheet resistance? So sheet resistance is nothing but rho S. And what is this rho S? Rho S is nothing but rho divided by T. Since thickness is something which is already given, rho is material quantity, so that is also known. So we also know this rho S quantity here when we are realizing these resistors on chip. So what the industries or what these foundries will give us is the value of this rho S. And then according to the desired value of R that we want to realize, we'll specify a particular value of the L, a particular value of W. Another way of defining these resistances on chip is based on the number of squares times this sheet resistivity. So what is the number of square? So basically each of this resistor is formed of different squares. And if we know the resistivity of one square, we just have to multiply that sheet resistivity times that number of squares. So that is also how people define resistances when they are realizing on-chip resistors. Also to reduce the area, I mean what people do is they use kind of serpent kind of structure to reduce the area and realize large resistances. Also in analog circuits we want our resistances to be as matched as possible, right? However, when you draw them on a wafer, what would happen if they are physically separated by certain distance? The ability of the tool to reproduce the same resistance will not be efficient, right? If they are separated by a large distance because of process variation, they won't be matched. So what people do in order to match these, they use these interdigitated type of resistors. So here what they do, they kind of combine, let's say what is first resistor? So first resistor is going like this, right? So it's going like this. So first of all, you see that it's kind of a serpentine structure. Why serpentine structure? So as to reduce the area while realizing a large resistance. And why they have connected alternate of these, alternate pillars, or I would say alternate individual resistances, because these alternate resistances, this would be very closely matched to this one. This would be very closely matched to this one. So if you are kind of choosing or connecting alternate resistances, you are kind of, overall the matching would be better. So the ones which are in the neighborhood, they are perfectly matched. But since we have to use this serpentine kind of structure, we have a very large resistance to realize. So what we do is we kind of connect alternate of these, individual resistances. And by doing that, we are trying to, reduce the mismatch error. So this kind of connection is called interdigitated connection. So these interdigitated resistors or interdigitated capacitors, they are like interdigitated capacitors are heavily used in your MEMS sensors. So your mobile phones, the sensors that are there in your mobile phones, the gyrometer-based sensors, or most of them use these interdigitated capacitors or interdigitated resistors. Now enough of these, talking about these resistors, on-chip implementation of resistors. Let's look at how we can implement MOSFETs as resistors. So we already know that in the linear regime, the MOSFETs are kind of voltage controlled resistors. Even in the saturation mode, they act like resistance. They basically act like current source, but with an additional resistance kind of thing, which is coming because of channel length modulation or because of that 1 plus lambda VDS parameter. So that is huge resistance. And linear regime, in linear regime, you can actually realize different values of resistors using a MOSFET. So what are the advantages of having MOSFETs as resistors? First, MOSFET occupies a pretty low area as compared to a resistor. So how exactly large resistances are realized? We use polysilicon and we use serpent kind of structure. So a MOSFET's layout, it looks like this, and the resistor layout looks like this. So you can see that to realize the same value of resistance, so we require a larger area for a polysilicon based resistor and a smaller area for a MOSFET. Also, you see, this is polysilicon. I mean, the gate is polysilicon over here. So this is the diffused area, or I would say this is your heavily doped source, heavily doped drain. These are two contacts, and this is your gate, which is your polysilicon. This is previous technology. Nowadays, gates are metal. But anyways, so you see, this is just for your information that to realize same amount of resistance value, the area occupied by MOSFET is pretty small as compared to the area occupied by these resistances when they are fabricated using polysilicon. Since area translates to cost, we also have low cost. Also, the implementation is more precise when you are implementing with MOSFETs. So since these are large structures, so in two large structures, amount of mismatch would also be large. In MOSFETs, the amount of mismatch, since they are placed close to each other, that is pretty small. So another advantage, which I would say is the bigger advantage of MOSFETs, is that we have two knobs, two controls. The current here depends upon gate and drain voltage. So by tuning the gate voltage or the drain voltage, you can tune the effective resistance between source and drain terminals of a MOSFET. Now let's say because of process variation, two MOSFETs which are bound, like which we want to act like resistances, are placed far apart on a chip, and we want them to be matched. So what we can do is, even because of process variation, if their resistance values are not matched, we can always tune their gate and drain voltages in order to match their resistances. So this tunability gives you an additional knob to control mismatch errors. Now also, if we have to fabricate only memories or only transistors on a chip, then it's ease while manufacturing also. See, because all these different components, when we want to realize them, they also require different masks. So what happens is that if you have different components on a chip, for instance, if we have MOSFETs, we have these resistances, we have some capacitance implementation on the chip, then basically we require different masks. And mask is something which is pretty costly. Why do we need mask? Because we have to carve these resistances on the silicon wafer. We have to etch it, we have to deposit it for etching or for deposition. And for defining these shapes, we need a mask in the photolithography process. So mask is something which is inevitable, and mask is something which is costly. So if we have like only one kind of component on our chip, let's say I'm realizing everything with the help of this MOSFET itself, be it resistance, be it capacitance, be it transistor. If everything is realized with the help of MOSFET itself, then it will be easier for manufacturing because then we don't need extra additional masks, right? So that is also one of the benefits while going for this kind of only MOSFET-based implementation of resistors. Also, if we require, like, since we are requiring lower components for fabrication, therefore, the cost is also less. So that way also it's beneficial for the industry. So now that we know that by replacing resistors via MOSFET in your chips, you can kind of reduce the area cost and you can also reduce the static dissipation. Let us go ahead and see what are the different available options for realizing these resistors. And then after analyzing those different options for resistances, we'll see how exactly these inverters will work with N MOSFET as the primary element and these different implementation of resistors using MOSFET as the load. So first of all, let us go ahead and look at the diode connected N MOSFET as one of the implementation of resistance. So this diode connected NMOS is something that you must have done in E210. So what exactly it is? So here your gate is connected to drain or gate and drain are shorted. So what exactly is M2? So M2 is enhancement mode transistor. Why enhancement mode transistor? If its threshold voltage is positive and it's an N MOSFET, it's an enhancement mode, right? Remember the discussion that we had? So M2 here is an enhancement mode transistor with a positive threshold voltage, and we have shorted its gate and drain. And since we have shorted the gate and drain, therefore it acts like a diode, and we call it a diode connected load. And we read about this gate drain shorted configuration in E210 that since here the VGS is equals to VDS, so the VDS will always be greater than VGS minus VT. So this transistor will be in saturation. However, it also depends upon the applied VGS or VDS. How? So if your VDS or your VDS is less than VT, the threshold voltage, then M2 will be in cutoff. Only when your VGS equals to VDS is greater than VT, then you can say that M2 is in saturation. So if you look at its ID VDS curve, which is like, it's a load line curve. So its ID is the current that is flowing through it, and VDS is the current across it. So if you look at its output characteristics, you see that, below VTN or below the threshold voltage of this M2, no current flows. The current starts to flow only beyond this threshold voltage. So its VTC, its output characteristics looks something like this. So now that we know the characteristics of this diode connected N MOSFET, let us look at the characteristics of the inverter in which this resistor is replaced by this diode connected load. So in such a scenario, this ID2 is same as ID. Therefore, this forms your primary element and this is your load. So for load, what we do? Similar to the resistors case, what we'll do is we'll just take its reflection, and then we'll just shift it by VDD. So once we do that, and once we plot the load line characteristics of M2 and overlap it with the output characteristics of this MOSFET or the primary element, N MOSFET or the primary element, we arrive at this plot. So here, these are the plots for different values of inputs. That is, VGS is your input of this NMOS. So these curves are the output characteristics of that MOSFET M1 for different values of inputs. And this is the load line of your diode connected load. And you one point that you should remember that it starts conducting only after this VTN or this threshold voltage of diode connected MOSFET. So the first intersection point, when your input is 0 or when your VGS is less than VTH, that is, the line coincides with this x-axis, right? So when your Vin is less than VGS, we say that the current is 0 and this line coincides with the x-axis. So for that, the first intersection with this load line is at this VOH value, which is VTH smaller than VDD. Why VTH smaller than VDD? Because if this Vout is greater than VDD minus VTH, then this transistor gets into a cutoff region and VDD is not connected to this capacitor, which is at the output. I mean, this Vout is simply the voltage across the load capacitor. So what is the maximum value till which this Vout can charge? I mean, till which the load capacitor can charge? What is the maximum value of Vout? So if Vin is 0, this is cut off. So this capacitor will start charging through this diode connected load. However, the moment this voltage, the source voltage of this diode connected load, this becomes VDD minus VTH of this diode connected MOSFET, what happens? The transistor, I mean this configuration goes in cutoff and no further current flows through this configuration to the capacitor. So the maximum voltage to which the load capacitor can be charged is VDD minus VTH. So another way of looking at it, so VOH is basically VDD minus VTH of this transistor. Another way of looking at it is there is always a drop of VTH in your diode connected load. I mean, you remember from E210 that there is always this, like, you know, a drop of VT once you go through it. So that drop of VT makes this voltage, maximum voltage achievable as VDD minus VT. So that is another way of looking at it. But the main concept behind this is that, you know, the moment this Vout increases beyond VDD minus VT, this transistor gets cut off, and as such, the connection between VDD and this load capacitor over here gets open. So there's no connection beyond VDD minus VTH. So the maximum voltage that the output can achieve is VDD minus VTH, and that is the VOH of this inverter configuration. Now for different values of VGS, similarly, we'll have different intersection lines. So we'll have value Vm where VGS equals to VDS equals to VGS equals to VDS equals to Vm. And then at the intersection 4, we'll have its VOL. Now let us look at the VTC of this inverter. So first, let us look at the case when Vin equals to VGS is less than VTH. So we know that for that case, your Vout is fixed at VOH, that is VDD minus VTH. So it's fixed at VDD minus VTH. Now let us take the case for Vin equals to VTH. So when Vin equals to VTH, what happens? This transistor just turns on, and for Vin equals to VTH also, the curve is along the x-axis itself. I mean, it's just above this x-axis. So even at that point, the Vout is pretty close to VOH. So from Vin equals to 0 till Vin equals to VTH, the output remains at VDD minus VTH. After that, what happens? There is this transition region. And then at the end, what happens? We get a VOL, which is not 0, but it is higher than 0. Also, a thing which is very important to note here, that, you know, for steep slope, what we exactly want? We want that for a narrow, so for steep slope in this VTC, what we want, for a narrow change in the input voltage, there should be a large change in the output voltage, right? So that is the meaning of steep slope. The change in the output should be pretty large as compared to change in the input. How does that translate to this load line? So for this load line, what should happen is, if the VGS is changing by small amount, I mean, you know, if this VGS is changing by small amount, then there should be large number of operating points there. So let's see that. I mean, let's see with the help of pen. Let me just open my pen and explain that to you. So let's say that I have this VGS equals to Vm. And let's say I have again VGS which is slightly higher than Vm. Let's say I have a VGS which is slightly lower than Vm. So ideally, if we want a large change in the output, like if you want a large change in the output voltage, so these curves correspond to input, right? These curves correspond to input. This is the axis where the voltage is changing. So in order to achieve an ultra steep swing or a very high gain over here, what we ideally want is that if it shifts by even, you know, this much amount, like if this curve shifts by even this much amount, there should be a large change in the output. I mean, the operating point should shift from here to here. There should be a large change. You understand what I'm trying to say? So this simply means that if the input is changing by small amount, let's say this is the change in the input voltage. So the change in the output voltage or the next operating point corresponding to this or the intersection with this curve should be somewhere here. Similarly, the intersection with this small voltage should be somewhere here for having a large change. So what we need is, for this steep swing, we need a characteristic something like this, and not, you know, a concave kind of characteristics. So that is also something which is very important, and I'll be discussing about it in detail. So first point that we can take from this VTC is the VOH drops to VDD minus VT. Now, another important point to note here is that, you know, we have neglected body effect till now. So since this is an NMOS, so its body will be connected to the ground, right? Since its body is connected to ground and the source voltage is increasing, effectively you are reverse biasing this body to source junction, right? So once you are reverse biasing this, your threshold voltage of NMOS increases. So if your threshold voltage of NMOS is increasing, this VOH drops further, right? Because of this body effect. So the body effect makes life more worse, I would say. So here, first, your VOH is already VDD minus VT, because if this VOH is charged beyond VDD minus VT, this transistor gets into cutoff, and this VDD is open, or this VDD is no longer connected to this load capacitor here, and it cannot charge it further. So first, VOH is already VDD minus VT, and second, because of this increase in this V out, the body effect also increases this VT value. So these two factors kind of degrade its VOH value. Second, we have a poor noise margin and a poor swing. Since your VOL is also high and VOH is also small, so the swing is already small. And since the swing is small, also the noise margins are pretty small. Now, VTC is not ultra steep. Why so? Because of the reason that I explained here. Load line is a concave curve like this. The change in the input leads to only a smaller change in the output. I mean, still the change in the output is larger than the change in the input because the gain is still high. I mean, it's larger than 1, but the specific change in the input for this case, like the change in the output corresponding to a small change in the input, is pretty small. However, if your load line was like this, I mean, if your input changes by a small amount and the operating point shifts towards larger value, or if the input reduces by a small amount and the operating point shifts here, then you'll have a large change in the output, even with a small change in the input. So we need a characteristics or a load line which looks like this. So let me draw it again with my pen so that it becomes. So we need a characteristics which looks something like this, right? Something like this. So we need a convex kind of load line. So we need a convex kind of a load line and not a concave kind of load line. I mean, we need this kind of load line for ultra steep slope and not this kind of load line. And if you practice making this yourself, you'll be able to understand it more clearly. Also, why this problem is happening? I mean, this body effect and all, why this is happening? This is just happening because this source node of this diode connected load is connected to V out, and that is changing. So if we can somehow make the VGS of this M2 independent of this source node or V out, then this problem won't occur, right? So there's one way of making it, independent of this source node. I mean, it won't get into the cutoff mode even if the V out goes to VDD, and that is by using a gate biased N MOSFET. So in a gate biased N MOSFET, what we do is we connect this drain to VDD, but we connect this V bias to VDD plus VT, at least VDD plus VT. We bias it to voltages greater than VDD plus VT. So here also we use enhancement mode MOSFET with a positive threshold voltage. However, we use a bias which is always greater than VDD plus VT. So if your bias is VDD plus VT, then what happens? If your bias is VDD plus VT, your effective VGS minus VT is VDD, which is same as the drain voltage. So this is in saturation. However, for even a small amount of voltage larger than this V bias, we will have M2 in a linear region. Why? Because this VDS, which is VDD, will be smaller than VDD plus VT, like will be smaller than V bias minus VT, since it is larger than VDD plus VT. So for this range of V bias, we see that it's not going in cutoff, and it's always in saturation or linear region. So it's never in cutoff. And till what value of this VS2 it can, if V bias is VDD is greater than equal to VDD plus VT. So even if this even if this source node of 2, that is VS2, is VDD, this won't go into cutoff region. So this is how we can make this transistor not get cut off, even if your source node is charged to voltage of VDD. So the maximum value of VS2 that we can have here by just biasing the gate voltage beyond this VDD or beyond this VDD plus VTH is VDD. I mean, we can work with VDD at the source node. So M2 will not get cut off. That is what we want. And if you look at its output characteristics, ID versus VDS characteristics, you will find that it starts from 0 itself. I mean, there's no VT, it starts from 0 and not from VT. So it's like this is in this away from cutoff even at even for VDS greater than 0. Now let us look at the inverter when we replace this resistor with the help of this gate bias and MOSFET. So we have this V bias, which is greater than or equal to VDD plus VT. So this is your primary element, this is your load, and let us draw the VTC. For drawing VTC, we know that first we have to draw the load line. So we just, what we do here. Here also we take the reflection with respect to y-axis, then we shift it by VDD, and then we plot it along with the output characteristics of this M1. So once we do that, we have a similar load line as compared to the previous case, with just the difference that, here the intersection point shifts toward VDD. So here it doesn't start with VTH. I mean, VOH doesn't start from VDD minus VTH. So that VTH is kind of, it's VOH is VTH higher as compared to the previous case. Or here it's VOH is VDD. Why VDD? Because even if this Vout is even if this Vout increases VDD minus VTH, this transistor doesn't get cut off and it continues to charge this load capacitor till VDD. If this V bias is VDD plus VT, and if this Vout is VDD, then that is the, and then this Vout, if it increases beyond VDD, then it will be a problem. However, since the supply voltage is only VDD, we don't care about that. And here, as long as the V bias is greater than VDD plus VT, we can reduce that VT drop in the VOH. So here, the first intersection point, when your Vin equals to 0 or Vin is less than VTH, even for those two cases, I mean Vin equals to VTH or Vn less than VTH, the intersection points lie at this x-axis itself, and they lie at this VOH, which is equals to VDD here. Similarly, we'll have intersections. So here also, you see that VOL is not equal to 0. However, we have increased the swing by increasing the VOH. So if you look at its VTC, it looks something like that. Instead of having VOH at VDD minus VT, we have VOH from VDD. And here, as long as it's below VTH, this MOSFET will not conduct, and the output will be fixed at VOH, and then it will start to transition towards VOL. And at VOL, which is non-zero, your input is VDD. So this is the kind of VTC that you expect. So with this kind of configuration, what we have done, we have first restored VOH to VDD. We have removed that VTH difference, but at the same time, the swing is still small because VOL is not 0. So ideally, we want VOH to be VDD, VOL to be small as 0, and then the output swing is large and the noise resilience is large. Here, the noise margins and like VOL, since it's larger than 0, noise margin will be smaller, swing will be smaller. Here also you will have this impact of body effect. So here also, the body effect could be there. I mean, since there's a difference between the source node voltage and this body which is connected to the ground, body effect will be there. But it won't degrade your VOH much, because here VOH is not dependent upon VTH. So that's one point where it is better than the previous configuration. Also here, since this load line is kind of a concave, so the VTC won't be ultra steep. So what we need to do is, we need to make the load line we need ultra steep slope here, like for ideal switch, it should be ultra steep, and we need VOL to be 0. So for that, we have to make, or we have to choose a load for which the load line is convex like this. So if it is convex like this, what we have is, for small change in this Vin value, we'll have a large change in the Vout value. So we want that, right? We want a convex kind of load line characteristics for steep VTC. And again, we also want this VGS of M2 to be independent of this Vout, because as Vout is changing, VS is changing, and body effect will lead to change in threshold voltage. So that leads to some amount of nonlinearity as well. So these are the two things that we want. So what people did was, people came up with this depletion mode MOSFET. So far we were talking about enhancement mode MOSFET. And how we define enhancement mode MOSFET. So if it's an MOSFET and its threshold voltage is positive, it's a enhancement mode MOSFET. If it's a PMOSFET and its threshold voltage is negative, it's an enhancement mode PMOSFET. How we define depletion mode MOSFET? So if it's a NMOSFET and if its threshold voltage is negative, then it's called depletion mode. Why depletion mode? Because if it's negative, if its threshold voltage is negative, even when the gate to source voltage is 0, even if 0 VGS is applied, there exists a channel, right? Why? Because VGS is greater than VT. VT is negative, so VGS, which is 0, that is greater than VT, and we'll have a channel here. So it will conduct current even for VGS equals to 0, right? It won't be in cutoff mode for VGS equals to 0. So the reason it's called depletion mode transistor is that, we have to apply a negative gate voltage. We have to apply a negative gate voltage in order to pull these electrons, like in order to repel these electrons away from the surface and send them back to the bulk. So here, how we turn off this device? We turn this device off. So at VGS equals to 0 volts, since VGS is greater than VT and VT is negative, you have a channel here between source and drain. So the current flows here. Now, we don't want, ideally, we don't want, if the input is 0, we want no current to flow through it. So how do we switch off this MOSFET, or how do we cut off the current between your drain and source? So we have to apply a negative voltage on this gate electrode to, repel all these electrons in the inversion region away to the bulk. So the reason why it is called depletion, because we have to deplete this surface of the electrons. Since we have to deplete this channel or the inverted channel of this MOSFET because of the negative VT, it's called a depletion mode transistor. So here what we have is, we have the gate and source shorted and VGS equals to 0, so that it's greater than VT. And since your VGS equals to 0, therefore, even for changing values of voltage at the source node, it won't affect it, because VGS is always 0. Even if the source node voltage is changing, it won't affect the operation. Since VGS is 0, which is greater than VT, it will always be out of the cutoff region. So it will never go into the cutoff region. If you look at its characteristics, so it's like output characteristics of this configuration, it looks something like this. So we have ID and we have VDS. So it follows a curve like this. So you can, visualize this as, when you have VGS greater than VT, this was the curve for enhancement mode. Here, since VGS is greater than VT, even though VGS is 0, since it's greater than VT, since VT is negative, we'll have a curve like this. Okay. So, but the problem, if we include this as the load, then we require two different types of MOSFETs, right? We need enhancement mode MOSFET because the primary element is still the enhancement mode MOSFET. It is only acting like the load for that, right? So we need two different types of MOSFETs even now. This is kind of difficult. I mean, it's difficult, but it can be done by only introducing one additional process step. So if you just implant this, change the doping of this region, then what you can do is you can kind of, get this, I would say, negative threshold voltage. So just by using one additional process step of implanting, you can actually realize two different kind of transistors. However, this is still a complex process and it's a costly process. That is for sure. As compared to the conventional process, this is a costly process. So now let us look at the configuration of an inverter using this depletion mode and MOSFET as the load. So you have this as the load and you have this as the primary element. So what we have to do, we have to just take the reflection of this on the y-axis, shift it by VDD, and then superimpose it on the output characteristics of this N MOSFET, enhancement mode and MOSFET, which is something like this. So if you have this, load line of this will look something like this. So you see that we have achieved a convex load line. At the same time, here, since its operation is always in, above cutoff regime, or it's always, it's never going to cut off because this VGS is 0 and its VTH is negative. So its dependence on the source node voltage has also gone down. So there's a promising approach, right? Because we have kind of, mitigated all the problems that we had in the previous approach. Also, since this is convex, you can see that for VGS equals to VM, you see large number of intersection points. So if the VM changes even by slightly, if it is slightly higher like this, you have this intersection point. And if the if the VGS, which is the input to this M1, if it changes slightly, so your curve will look like this. So your intersection would be somewhere here. And if your VGS changes slightly lower, so if your output characteristics like this, so what happens? The intersection is at this point. So just for even a small change of V in close to this VM value, you see the operating points are separated by large value in the V out. So this gives you ultra steep slope as well. So if you look at its VTC, first here your VOH is VDD. Why VDD? Because this transistor is not going to cut off mode for any value of this V out less than equals to VDD. So this load capacitor will charge to VDD through this diode, depletion mode MOSFET. So till V in equals to VTH, your V out is equals to VOH, which is VDD. And then you have a ultra steep slope close to this PM just because of this convex kind of load line of this depletion mode MOSFET? And also, what about the VOL? So VOL here, although it's not zero, but it's smaller as compared to the concave type, right? Because in concave type, you had a characteristics like this, and your VOL was larger. So let us summarize. So our VOH is restored to VDD, our VTC is steep, and our VOL, however, our VOL is not zero. And what about body effect? So even here, what we will do is we'll connect this body junction to the most negative voltage, which is ground. So here, because of Vout, we will have body effect. So we'll still have body effect, but its impact will be small. However, for this VOL to be as small as possible, what is VOL? So VOL is kind of the voltage drop across this MOSFET when this Vin is VDD. Since this VOH is VDD, so when Vin is equals to VDD, Vout is simply the VDS value, right? So if you take this, if you represent them by their equivalent resistances, so it's simply VDD multiplied by equivalent resistance of M1 divided by equivalent resistance of M1 plus equivalent resistance of M2. So if you want your VOL to be as small as possible, you want the resistance of M2 to be pretty high, right? Only if the resistance of M2 is pretty high, then what happens? Or if the resistance of M2 is pretty high as compared to resistance of M1, then your Vout is pretty small. So we also saw in the previous lecture where we were calculating the equivalent resistance that this was proportional to what? This was proportional to W by L. I mean, R was proportional to 1 by WL. So if R is proportional to 1 by WL, we have to increase the ratio of W by L of 1 so as to reduce its resistance as compared to W by L of 2. So for having a low VOL, we need the equivalent resistance of this M1, then Vin equals to VOH, that is VDD, to be as small as possible as compared to RM2. So for that, what we can do in terms of design parameters, we can increase the W by L ratio of this so as to reduce its resistance as compared to the W by L ratio of M2. So by that we can reduce the VOL, but since we are increasing the W by L ratio, we are kind of increasing the W of this M1, and as such we are kind of increasing the A. So this is one trade-off which goes when reducing the VOL of this kind of configuration. However, it gives you a VOH which is close to VDD, and it also gives you a very steep slope. So that way it's very promising. Now, can we have this kind of characteristics, and can we also have a pretty small VOL? So that is something that that will make our lives more easy. So let us look at P MOSFET as the load. So till sometime, I mean till 1970s or so, people were only working with N MOSFET. So they thought about making this convex kind of load line, and they came up with this depletion mode N MOSFET. But later they realized that they can also produce this P MOSFET, and inherently this P MOSFET will show a load line which is convex. So let us look at that P MOSFET as load, and this kind of configuration is also called a pseudo NMOS configuration. I mean, the circuits that you make using P MOSFET as load with its gate shorted to the ground, that is known as pseudo NMOS based logic. So here what we are taking is, an enhancement type P MOSFET. For enhancement type P MOSFET, VTH has to be negative. So its VTP is negative. And what you have done is, you have connected the gate to the ground, and source is always connected to VDD, right? That we saw earlier. So what can we say about the VSG? So here, as I told earlier also, we talk about VSG. Since your gate is always grounded, since your source is always connected to VDD, your VSG is greater than VTP, right? Mod of VTP, we talk about mod of VTP. You remember that? We were discussing about P MOSFET, we told that we always talk about VSG, we always talk about mod of VTP, and we always talk about VSD. And the current here also, IDS is kind of ISD. So we also talk about ISD, which is positive. IDS is negative, ISD is positive. So, yeah. Since VSG here is greater than mod of VTP, so our M2 will not be in cutoff. So it won't be in cutoff. That is what we want, right? And also, it's independent on the voltage of this output node, which is the drain, when connected in the inverter configuration. Why so? Because this VSG is always greater than VDD. Since S is fixed, G is always grounded. S is connected to VDD, G is always grounded. So this is also not, this won't be in cutoff ever. So if you look at its characteristics, how we will plot its characteristics? So ID here is ISD, which is positive. So ID here is positive. Like here we have plotted VSD and not VDS. So if you plot VSD, you get a positive current. And what is VSG? So VSG is nothing but V supply, which is VDD. So you get a curve like this. So if you had drawn IDS, if you had drawn IDS, that is this current, and if you had drawn VDS, so the curve would look like this, right? This is characteristics of PMOS. But since we are talking about ISD, we are talking about this axis and not this axis, which is IDS, and we are talking about VSD and not VDS, which is this axis. So the curve is like this. Okay, now that we know it, let us look at the configuration, how we can implement the inverter out of it. So we use this P MOSFET as load and this N MOSFET, enhancement mode N MOSFET as your primary element. Here also what we have to do, we have to just take the reflection of this, shift it by VDD, and then superimpose on your output characteristics of this primary element for different values of V, which is the VGS, and for different values of VDS, which is nothing but the Vout. As was for the previous case, here also we'll have to make two different types of MOSFETs, and fabrication technology was like, when it got better, we had the capability to make two different types of MOSFETs, and actually it led to a revolution, I would say. So this eventually led to the invention of CMOS circuits, which led to a revolution, I would say. So that revolution was like, the circuit performance improved significantly. So even if realizing two different type of MOSFET was leading to two different masks and let's say some amount of process complexity, since the performance of the circuits was so good, people actually went for it. They bought that idea. So here, if you look at the superimposition of the load line, which is this, with the output characteristics of this MOSFET for different value of V, that is this, we find out that VOH is VDD, so Vin equals to 0. What happens? This is cut off, and this load capacitor can get charged to this VDD from this P MOSFET as load, because this is never going to be in the cutoff mode. Irrespective of the drain voltage, since this VSG is always positive, this will always conduct, and this load capacitor will be charged to VDD. So till the Vin is equals to VTH, this output remains at VOH, which is VDD. So which is this. Here also, since it's convex, therefore the slope is ultra steep. Here also your VOL is pretty, like here VOL is small as compared to concave load line, but it's still not 0, right? So advantages, we have restored VOH to VDD, or VTC is steep, but VOL is not equals to 0. However, the advantage here is that in your PMOS, your source is also connected to VDD. So if your source is also connected to VDD, here is no body effect. So some amount of non-linearity that may be introduced by this body effect, that is also not. Also, this VOL is not high, even if the MOSFETs are minimum size. The reason being that, here in depletion mode MOSFET, if their size, if the W by L ratios are equal, then their resistance is kind of same, right? If the resistance is same, then the kind of same, it's not exactly same, but they're comparable. If the resistance is comparable, then the VOL will be large, because it's simply RM1 divided by RM1 plus RM. But here, what happens is, because this mobility of PMOS, mobility of holes, since that is smaller as compared to the mobility of electrons, the inherent resistance of this P MOSFET is larger as compared to the inherent resistance of this N MOSFET. How much larger? The ratio between them is the ratio of the mobility of holes to that of electrons, and that is close to 2. So I'll be discussing this when I'll be discussing about the CMOS inverters. So even if the sizes of these two transistors are same, that is W by L of 2 is equals to W by L of 1. Just because inherently the mobility of the majority carriers that are holes over here is smaller as compared to the majority carriers, mobility of the majority carriers, which are electrons here. Therefore, the resistance of this is larger by at least 2 times as compared to the resistance of this, even if they are minimum size or even if they are same sized. So that helps it. We can make it even small, like minimum size, both of these MOSFETs even minimum sized, and still we can have a low VOL as compared to the depletion mode MOSFET case. Why the mobility is larger for electrons as compared to holes, that we shall discuss when we are discussing the delay of CMOS inverter. So in the next lecture, we will be discussing that. However, we have been using this as a load, but we know that this is a positive switch and this is a negative switch, and we know that if we if we connect a negative switch to a positive switch in series and we apply input to both of them, then that also acts like an inverter, right? So why don't we do that? Instead of utilizing this as a load, why don't we connect this to the input and then see what happens? So that configuration where inverter, where N MOSFET and P MOSFET both are acting like switch, and where this P MOSFET is at the top, N MOSFET is at the bottom, this is called CMOS inverter. Why CMOS? Complementary MOS inverter. Why complementary? Because N and P MOSFETs are complement of each other. Therefore, these circuits are called complementary MOSFETs, the complementary MOSFET circuits, CMOS circuits. Also, we looked at, while defining inverters with switches, we found out that, if we stack a negative switch on top of a positive switch and give common input to both, then this acts like an inverter. So this configuration is nothing, but it has, a positive switch and a negative switch with a common input. So we have a positive switch, which is this, and a negative switch in series. If you look at the input, this input can be simply defined as, what is this input? So this input is VGS of N, or what is VSG? So VSG is VDD minus Vin. So from there you get Vin is equals to VDD minus VSG of P, right? So Vin is nothing but VGS of N or VDD minus VSG of P. What is Vout? Vout is VDS of N, or what is this Vout? VDD minus Vout is VSD of P. So from there you get Vout is VDD minus VSD of P. So now if your Vin equals to 0, what happens? This is in cutoff. So this switch is open. However, if Vin equals to 0, since this is a negative switch, what happens? This connects VDD to this Vout with a small resistance RP, and hence our Vout is 1. When Vin equals to VDD, this is off, this is in cutoff mode, and this switch is on, and this Vout is connected to ground with the help of this RL. So if you look at its VTH, or if you look at its VTC, here you find that for Vin equals to 0, Vout equals to 1, Vout equals to VDD, because this VDD will be connected to this point, and there will be a load capacitor which will charge to VDD through this PMOS, since this PMOS will conduct when Vin equals to 0. And when Vin equals to 1, that is Vin equals to VDD, this Vout, this will be turned off, this will be in cutoff, and this Vout will be discharged, or the load capacitor here would be discharged to the ground through this M1, since M1 is conducting when Vin equals to VDD. So here your VOL is 0, your VOH is VDD, and also between 0 to VTH, since this is not conducting, this Vout remains at VDD. Also, between Vin equals to VDD minus VTH to VDD, since this is not conducting, this Vout remains equals to 0. So here we have 0 slope between 0 to VTN and VDD to VDD minus VTH of P. So we have 0 slope in this region in the acceptable logic levels. I mean, till this point, till VTN. This is also a part of the acceptable logic level. So acceptable logic level is still your VIL and VIH, but as long as the Vin is less than VTH or Vin is greater than VDD minus mod of VTHP, you see that the slope is 0. And in between there is a steep slope. Why? Because the characteristics of this PMOS would be like this. I mean, we'll show it in the next lecture. So just by looking at this inverter, what we can say is it has got full logic swing because Vout is VDD, like VOH is VDD, and VOL is 0. We have steep transition at PM because PMOS inherently exhibits a convex kind of characteristics, and we have 0 slopes at VOH and VOL. and then we have a high slope in between. So this is something which is very close to the near ideal, like to the ideal switch, or ideal, I would say, not ideal switch, ideal inverter. So since its VTC is very close to the ideal inverter VTC, we'll be diving deeper into the operation of these CMOS inverters, and we'll be looking at, how the delay, how the power, and all those things are related, or how we can reduce it, how we can design a CMOS inverter for making symmetric VTC